All right, in these next two sections, we are going to take a look at vectors. So here are all of the goals for this section. So the first thing we want to talk about is, well, what is a vector? Right? Lots of physical quantities, such as length, area, volume, mass, temperature, we can completely describe them by a numerical value, okay, by their magnitude. Length, 5 feet, area, 23 square inches, temperature, 76 degrees Fahrenheit. These are called scalar quantities. Other quantities are only completely described if we have both a size and a direction. Okay? Velocity, force, acceleration. Right? These we use vectors to describe. Right? So I'm sure you've seen in your science classes, the difference between speed and velocity. Speed would be saying something like 25 miles an hour. Velocity would be 25 miles an hour due west. Right? Velocity includes speed and direction. All right? So to represent a vector, we use a directed line segment. Right? So it just looks like a ray. So we can draw, I'll just draw a random one, something like that, right? Where we have an initial point and a terminal point. Right? The initial point on this graph would be represented by the dot. The terminal point would be represented by the arrow. So sometimes we'll be given names for these. Right? We can say this is A and the end here is B. So there's a few different ways that we could denote this. Okay, we could say something like this, AB with a little vector symbol over top. Sometimes you'll see it drawn as a full arrow, but other times you'll see it drawn just as like half an arrow, like that. Now, another very common way to denote vectors is just with a single lowercase bold letter. Right? So we could say like a bold V would denote this vector. Okay. Now, component form of a vector is going to be very useful for what we're going to be doing with the math behind it. The component form just breaks it up into an x and a y coordinate. Okay, so, or more accurately, a change in x and a change in y. So for this vector here, we're just looking to see, well, how far did we go to the left or right, and then how far up did we go to get from the initial point to the terminal point. So in this case, starting here and ending here, we went 1, 2, 3, 4, 5, 6 over. So my change in x would be a positive 6. And direction does matter, right? So if I went to the left, it would be a negative 6. Then I'm going up 2. So the component form of this vector would look like this. Now, the magnitude is just the length of the vector. So really all we're doing here is finding, if I know the components, 6 and 2, I'm essentially finding the hypotenuse of a right triangle. So all we would need to do is say that, well, I guess first I should talk about notation. Okay, the general notation is to use double bars. Right? This is how our book does it. Now we could also potentially see just single bars. Right? That's another way to denote magnitude, but this is how our book does it. So this is how we're going to use in our notes and on quizzes and tests and things. So the double bar around the vector means find its magnitude. So all we're doing is using Pythagorean theorem. So Pythagorean theorem is a squared plus b squared equals c squared. So we can solve for c and say it's just going to be the square root of these two values squared. So for this one, the square root of 6 squared plus 2 squared. So that'll be the square root of 36 plus 4, square root of 40. And then we can, simplify this. This would split up into the square root of 4 and the square root of 10. So we can say the magnitude of this vector as an exact value would be 2 times the square root of 10. Right, so the magnitude is just the length of the vector. Right, so let's go through a kind of a full practice problem with those ideas. So here we're given 2 points, an initial point and a terminal point. So let's sketch out what that vector would look like. Right, so it's saying we're starting at the point 7, 2, 7, and ending at the point 3, 5. So the vector would look something like that. Right, and they gave us names for the points. So this is P, and this is Q. So there's our sketch. So now it says write this in component form. So I just want to think about how far left or right did we go, and how far up or down. Right? So we're going like this. So to get from P to Q, I would go left 4. So my x portion of this vector would be -4, and then I'm going up 3. So this would be my PQ in component form. The final thing we want to do is find the magnitude. So magnitude of PQ is going to be the square root of -4 squared plus 3 squared. So that's 16 plus 9, which is 25. So the magnitude, or the length of this vector, is just 5. Okay? Next, let's talk about scalar multiplication and adding and subtracting different vectors together. Okay, so let's say that we're given these two vectors, a and b, and the components of a are just a1 and a2, and the components of b are b1 and b2, and then k is just a number, okay, or a scalar. We can say that if I multiply a times that scalar, all I do is multiply each of the two components. All right. So we'll do a concrete example of this next. Okay, but if I'm multiplying a vector by a number, all I do is multiply each component. If I want to add two vectors together, if I want to add a plus b, all I'm going to do is add the two x components together, so a1 plus b1, and then add the two y components together, so a2 plus b2. And then same thing if I want to subtract. If I want to do a minus b, all I'm going to do is subtract the x components and subtract the y components to get my new components here. All right. So let's go through an example with some of those ideas. So let's say that we're given a is 2, -4, and b is -5, 3. All right, we want to find a plus b, a minus b, 7 times a, 2a plus 3b, and then the magnitude of 2a plus 3b. So, all right, so for a plus b, all I'm going to do is add 2 and negative 5 together. For my x component, so 2 plus negative 5 would be negative 3, and negative 4 plus 3 would be negative 1. Okay, so I want to talk about what this means graphically as well. So let's say that we have the vector 2, negative 4. So I'll just start from the origin. Let's say I'm going 2, negative 4. So here's what that vector would look like. To add vectors graphically, what we do is take our second vector and start it at the end or the terminal point of our old vector. So we're saying from here now, I'm going to go negative 5 up 3. So negative 5 up 3. Okay, so graphically, this is how we would add vectors together. So now the n, or the result, is going to be from here to here. Okay, so if this was my vector A, and then I added vector B to it, this is the result. Okay, and we can see that we're going left 3, down 1. Okay, so the resultant vector is just adding these two vectors together. Right, so we're algebraically just adding the x components, adding the y components. Graphically, what we're doing is taking one of the vectors and then putting the other one, the initial point, at the first one's terminal point. Okay, then connecting that initial to that terminal. That gets me my final vector. All right. So if we're doing a minus b, I would take 2 minus negative 5. So 2 minus negative 5 is going to be 7. And negative 4 minus 3 would be negative 7. So to subtract vectors graphically, let's get rid of that one. Oops. To subtract vectors graphically, all we're going to do is put both initial points in the same spot. Okay, so to add them, I started at the terminal point. To subtract them, right, I'm going to take, this is still my A, I'm going to take B and start at its initial point. So I'm going to go from here, I'm going to go negative 5 up 3. Now, if I connect these 2 points, come on, there we go. Now if I connect those 2 points, I get this vector, okay? 7, negative 7. All right, so to add them, we're going tip to tail. To subtract them, we're going tail to tail. All right, but algebraically is pretty straightforward to do. Then if I want to use a multiple here, okay, a scalar, all I'm going to do is multiply each individual component by 7. So 7 times 2 is 14. 7 times negative 4 is negative 28. Now, I can use scalars and addition, right? So if I want to, let's first multiply a by 2. So that would be 4, negative 8. Oops. And then if I want to multiply b by 3, I will have negative 15, 9. Now I can add each of these components together and get negative 11, 1. So 2a plus 3b would be negative 11, 1. Now, if I want to find the magnitude of that vector, right, I already have its x component and its y component. All we're doing is finding the length. So that's going to be the square root of negative 11 squared plus 1 squared. So that'll be the square root of 121 plus 1, which would be the square root of 122. And I don't think that simplifies, so that would be our answer for the magnitude. All right. Next, okay, I'm just going to talk about another small notation idea. All right. First, if you ever hear the term unit vector, okay, a unit vector is just a vector of length 1. So, general notation, okay, if we've got a vector going 1 in the x direction, we call that I. And if we've got a vector going 1 in the y direction, we call that j. Okay, these are called standard unit vectors. So what we can do with that, okay, we can say we've got the vector, I don't know, 4, negative 7. Well, we can use these I and j ideas to write this vector in a different way. We can say that this vector would be 4i minus 7j. Okay. Let's say that we've got the vector negative 3, 1. Well, we can write that as negative 3i plus 1j, or just plus j. Okay, so just another little notation idea. We can write vectors using I and j notation, and you'll see that on the homework as well. But just understand that this means the same thing as this. All right. So the reason now that this is part of trigonometry, let's get into some of these problems. So if we are given a vector, we can find the angle that it creates with the horizontal. So to do that, we're going to use tangent, but essentially we're going to just set up a right triangle. All right? So let's draw a picture here. So here we want to find the directional angle represented by the vector 2, negative 5. So 2, negative 5 would be a vector that looks like this. All right. So what we want to find is the angle that is created. Essentially, we want to find this entire angle right here. Okay, well, to do that, we are just going to create a right triangle. Right, I'm going to create the right triangle right here. So if we know that this is the vector 2, negative 5, I already know these pieces of the right triangle. And what I want to find is this angle right here. So let's call that theta. All right, so this angle right here is theta. Well, what we want to think about is to find theta, we know the opposite side and we know the adjacent side in this triangle. So we can say, well, theta is going to be equal to the inverse tangent of negative 5 over 2. And we can put that into the calculator. So inverse tangent of -5 over 2. And again, make sure you're in degree mode. So I get -68 points. Let's go to the nearest tenth. So -68.2. So what that means is from here to here is an angle of -68.2 degrees. Right? If we're just thinking in terms of this triangle, that would be 68.2. Well, if my goal is to find this entire angle here, starting at the positive x-axis and ending on this vector, we want to think about taking 360, right, and either subtracting -68.2 or adding -68.2. So my red angle here is going to be 360 minus 68.2 degrees. So I think that would end up being, 291.8 degrees. So this angle, my directional angle, is 291.8 degrees. All right. So now let's use similar ideas, but we're given a little bit different information on this problem. Okay, this one says we're given that the magnitude is 5, and the angle that the vector makes with the x-axis is 120 degrees. So we want to find then the component form of the vector. So what we know now is, well, we've got our vector up here. We know that this angle is 120 degrees, and we know the length of the vector is 5. Well, if I want to find the x and y components, I'm going to create a right triangle here. So if I know this angle is 120, that means this angle here would have to be 60 degrees, right? So now, to find the components, we want to think about, well, this is my x and my y. To solve for x, if I know the hypotenuse, I could use cosine because I would be dealing with the adjacent side and the hypotenuse. So I could say the cosine of 60 is equal to x over 5. Or solving that then for x, we just get 5 times the cosine of 60 equals x. And we can put that into the calculator. 5 times the cosine of 60 is 2.5, because the cosine of 60 is 1/2. So the x component is 2.5. Do the same thing for y. So we'll end up here, since we're dealing with opposite and hypotenuse, that'll be the sine of 60 equals y over 5. Solve for y. So 5 times the sine of 60 is equal to y. So 5 sine of 60 is 4.3. So the question says first write it in component form. So the component form of V would be, we are going in the negative x direction, so negative 2.5. Okay, so make sure that you're paying attention to what direction you're going. Right? Since I'm going to the left, my x component is negative, and then 4.3. Then we could also write this in terms of I and j. I could write it as negative 2.5i plus 4.3j. Right? So if we look at these two processes that we use to solve for x and y, what we ended up doing is multiplying the magnitude times the cosine of the angle to get x, and the magnitude of the sine of the angle to get y. That's always going to be true. Okay, that's always going to be true whenever we're solving for these types of problems. All right, so magnitude times the cosine of the angle to get x, magnitude times the sine of the angle to get y. All right. So the last thing that we want to look at is a story problem, essentially. All right. So it says two forces of 200 pounds and 500 pounds act at the origin and make angles of 30 degrees and 45 degrees, respectively. Find the resultant vector. So what we're saying is there's some object right here, and we've got one force that's 200 pounds pulling at a 30-degree angle, and one force that's 500 pounds pulling at a 45-degree angle. What we want to find is what direction is that object actually going to go. Right? So the resultant vector, what we want to do is find the components of each of these individual vectors and add those components together. Okay? Add those components together. So if we know first, let's look at this triangle here. Okay, so we know that this is 200 and this is 30 degrees. So from that, I want to find the x and the y components. Right? So we can say that x is equal to the magnitude times the cosine of the angle. And we can say that y is equal to the magnitude times the sine of the angle. So let's put both of those into the calculator. 200 times the cosine of 30, 173.2. And 200 times the sine of 30, is 100. Then we can do the same thing with the other vector. Right? So I guess first we could write this purple vector in its component form, 173.2, 100. So then, let's do the same thing with this one. So I know that this one has a magnitude of 500. So x will be 500 times the cosine of 45 degrees. And y will be 500 times the sine of 45 degrees. So I know that both sine and cosine of 45 are the same, so we just need to calculate this once. 500 times the cosine of 45 is 353.6. Okay, so we can do a few things with this information. First, if I add the x components together and add the y components together, I will get the resultant vector. All right, so adding 173.2 plus 353.6 gets me 526.8. And then adding those two together would just be 453.6. So the magnitude then of this resultant vector. We can say it's going to be the square root of the sum of these squares, so 526.8 squared plus 453.6 squared. So 6.8 squared plus 453.6 squared gets me 695.2. So what we just determined there, right, this is the component form of the resultant vector. If I've got these two forces acting on this object, right, 200 pounds in this direction, 500 pounds in this direction, the resultant force is 695.2 pounds. It's not 700 pounds, as you would kind of think, right? If you've got these two forces, you would just add them together. But no, it's 695.2 pounds. All right. We could actually also then find the angle that resultant force is created. We could say that that would be the inverse tangent of my y over my x. So inverse tangent of 453.6 over 526.8. So that will get me an angle of 40.7 degrees. So if these two forces are acting on some object, the end result will be this object is being pulled or pushed, whatever is happening, with a force of 695.2 pounds at an angle of 40.7 degrees. All right? So this kind of stuff is how vectors are pretty useful. Okay? Force is one of the biggest applications. So there's a few problems I want you to try out of the book for tomorrow. And then there's also a bonus opportunity. If you want to get some bonus points, try some more of these story problems, you can make a Khan Academy account and join my class and then complete the vector word problems. Right, so the instructions for that are on the Google Doc and on Schoology. And as always, please send me any questions that you have.